Hey everybody, welcome to my Physics 2211 Lab Report 3 Black Hole. For table of contents, we're going to be doing instructions and some underlying physics principles. We'll be going into the computational models for the black hole for both part 1 and 2. Then we'll be doing some discussion and talking about sources of error. Then we'll be doing our conclusions and questions raised, which are the what if and what's if questions. So first, for the purpose of this lab. First, this lab is to analyze the effect of universal gravitation by the following. First is finding the mass of the black hole by using a star's orbit around it. So that's using the gravitation formula and deriving one of the parts of it, which is M2 of the traditional formula. And then the second part is determining the initial speeds in the x and y directions necessary for a spaceship to fly around a black hole without crashing into it or the planet the ship launched from. So we're trying to get off of Midler's planet and Interstellar without getting anybody killed. So that's actually really fun. And then this will be done using the following physics principles, which is Newton's second law, universal gravitation, and orbital forces, which are the Fnet in the parallel and perpendicular directions. So some foundational physics first. So we're using Newton's second law in this lab report. So we know the mass of star and starting velocity, so we can calculate change in momentum throughout the rotation of the star. That applies to part 1. And then for part 2, then we'll be using the very same formula to calculate the effects of gravity from the star from the black hole and from the planet on the ship, and then from the ship and the black hole on the planet. And then we're also going to be using universal gravitation, F equals G M1 M2 of R squared. And specifically, we're going to be switching all the components to the left side of that formula. So we'll be dividing both sides by G and M1, and we'll be multiplying both sides by R squared so that we can get M2 by itself on the right side. That'll be used for part 1. And then for part 2, we'll be using that formula to calculate the forces of gravity in order to determine how the ship and the planet are going to move in relation to the black hole. So we're also going to be using orbital forces, which is something new for this lab, and that is F parallel and F perpendicular. So we're building on lab 1 and 2. F perpendicular and F parallel are critical factors in determining the change of momentum over time for both models. F parallel results in changes to the magnitude of momentum, and F perpendicular results in changes of direction to the momentum of the object. And we'll get more detail on that later. So system and surrounding. The system for part 1 is just the star, and the surroundings for part 1 are the black hole and space. And so that means that the black hole is exerting forces onto the star, thus the surroundings are affecting the system. And for system for part 2, we have the spaceship being one system, and then the planet being a separate system. We calculate forces on both of those. So the surroundings for part 2 are space and the black hole for both of the systems, then the planet, which only affects the spaceship system, and the ship, which only affects the planet system. And a brief preview of findings is that for part 1, I found that the mass of the black hole was about 1.76 times 10 to the 34 kilograms, which is very heavy. And then part 2 was the initial speed of the spaceship was determined to be -9 times 10 to the 7 meters per second in the x direction, and 1.9 times 10 to the 6 meters per second in the y direction. I did that with primary error. So for part 1, planet orbiting black hole, these are our initial conditions. So we have the star's mass, which is given. We have G, the gravitational constant, which is also given, and then we calculated delta T for a full day, which is what we were asked to do. All right, and then this is some of our code. So as you can see, we're solving for momentum, which is P. So P initial is V initial times the star's mass, so P equals mv. We know that from Newton's second law. And then P finals uses the same formula. So for delta V, we then use V final minus V initial, which we already know. And then for delta P, of course, any change in any value is going to be final minus initial, right? And so then we have dP dt, which is delta P over delta T, right? So that is your change in momentum over time. And then F net is the same as your change in momentum over time, which is actually important for our what if, or for our what does it mean question later. And then we solve for P hat, d mag pdt, and dP dt parallel. And so those values are very important for creating our model. And we just have a little bit more here. I'm running out of time, so I'm just going to let y'all see this. The most relevant thing on this slide is the mass of the black hole, which we're ultimately trying to solve for. And you just do the algebra I described in my underlying physics slide, and that's how we derive that formula there. Oh, and I also added some printing here, so I wouldn't have to manually calculate Fnet values, like Fnet verb values, which goes at the end. So, ultimately, part 1, the average of the masses of the black hole at all intervals came out to be 1.76 times 10 to the 34, and magnitude of Fnet was 9.814 times 10 to the 28 newtons. If you're curious, you can see in the bottom right the vector for that value. And then for the magnitude of F perp, 9.811 times 10 to the 28 newtons, and the magnitude of F parallel was 3.065 times 10 to the 27 newtons. The force of gravity between the black hole and star weakens as distance increases. That's intuitive, right? Like gravity has more of an effect the closer you are to an object, because R squared is negatively correlated to forces, right, in the gravitation formula. So that, if you watch the video, which all y'all made this model as well, then the arrows representing forces increase in size as the distance between the black hole and star decreases. So as it's on the left side of that circle, then you can see the arrows get really big. And then F perpendicular becomes much stronger as the planet approaches, which is why it gets closer. So F perpendicular is kind of pulling the star closer to the black hole. Oh, then for part 2, we're launching off of Miller's planet from Interstellar, right? So these are our initial conditions. You can see the ship speed and X and ship speed Y. Those were the ones I decided on. I attained those through trial and error. But the initial conditions and Tmax, which I calculated to be 3 minutes, you can see here. And I'm gonna be a little less detailed here because of time, but as you can see, the distance between the black hole and the planet is just the position of the planet minus the black hole's position. That's the same way we calculated the distance between ship and planet. And then the force of black hole on planet, force of ship on planet, all that's just using the gravitation constant or the gravitation formula we've already discussed. And then F net, of course, is the sum of all forces, right? And that's the same for the spaceship, which I've also included here. And then we have planet velocity. This is actually an application of the velocity update formula. So planet's velocity plus F net divided by m multiplied by delta t. That's the velocity update formula. And then the position update formula using non-constant forces is how we did the planet position there. And ship velocity and ship position is calculated in the same way. And then you can see these error messages. I'm sure y'all ran into those a couple times as well while you were playing around with initial velocities. But yeah, that's the code. So ultimately, we ended up getting the graph on the right side. So I sort of just did a quantum catapult. If any of y'all are into science fiction, the ship got launched by the black hole super fast out of the system. So I decided upon an initial velocity of -9 times 10 to the 7 meters per second in the x direction, and 1.9 times 10 to the 6 meters per second in the y direction. So we got a really fast ship. We've advanced technology quite a bit. And then the closest distance between the spaceship and black hole was 2.1 times 10 to the 8 meters, which is actually super close relative to astral bodies, right? And that's where our ship got slingshotted. So it's where the ship's right next to the black hole, as you can see from the model on the right side. So the spaceship exited the system at a very high speed, faster than the initial, due to the black hole becoming a slingshot, right? So I'm gonna go to the top right here. Some possible sources of error. Our sources of error are somewhat limited because we're using models this time, thankfully. So there's no experimental error. There can't be any human error aside from rounding and calculated values. So my values for part 2 might be a little off because I rounded the black hole's mass for part 1. And then of course, if we were more precise with the gravitation constant g, then we would have more precise values. But it's not super big deal in this case. Well, our what does it mean question was, in your analysis, you discuss how the net force and parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. So this is just quizzing us if we know that F net and change of momentum are the same thing, right? So the rate of change of momentum is delta p over delta t, and we know from Newton's second law that F net equals delta p over delta t. So those are the same thing. And then for our what if question, instead of wanting to take a quick look at the black hole, you want to enter an orbit, right? So this was once again just kind of guessing and checking with the velocities, but intuitively we're going to need a faster y velocity and a slower x velocity because we don't want to use the black hole to slingshot us out of the system. We want to orbit it, right? So we're going to try to stay away from the black hole and the super powerful gravitational forces. And so the velocities I ended up using for that are negative 2.7 times 10 to the 6 meters per second in x and 1.1 times 10 to the 7 meters per second in the y. So I hope you all learned a little bit about physics and enjoyed this lab. Thanks.